Hi, in this lecture I will be focusing on the basic principles of digital signal processing along with basis of DSP, some knowledge on DSP processors, DSP applications, how DSP works, and some discussion on sampling, quantization and coding. Okay, we can start with the basic principles of digital signal processing. And for that, I will be focusing on the block diagram of the basic principles of DSP. You can see over here that this is a block diagram of a digital signal processor, and these are the sub blocks. Whenever the signal is transmitted by the transmitter, it receives noise from transmitter itself, including the environment, and the receiver. This is the block diagram of the DSP processing on the side of the receiver. The signal, which is in analog form, comes over here, and that signal is exhibiting the noise, and it is being amplified over here, and then the signal will be in the continuous time domain, and this signal is sent to the A to D converter, which is doing the conversion of the analog signal from analog form to digital form, and the continuous time domain signal is converted into the discrete time domain signal. As you can see over here, these are the samples of the digital signal, and afterwards this time domain discrete signal is sent to a kind of environment in which the program of the computer is having this kind of instruction of DFT, which converts the discrete time domain signal into the discrete frequency domain signal, and then this discrete frequency domain signal is received by the ZT filter, which is the instructions of the computer program of the digital signal processor, and that is isolating the noise in the frequency domain, reducing the number of samples of the frequency in the discrete domain, and then the reverse process starts. After the noise is removed, it is isolated by the ZT filter in the frequency domain. Now the time is to convert the signal into the actual form from where it was received from the environment, and then the IDFT instruction of the computer program is converting that discrete frequency domain signal into the discrete time domain signal, which is then later sent to the D2A converter, which is converting that discrete time domain signal into the continuous time domain signal. And afterwards, the signal which is received over here is not a kind of pure analog signal. It is a kind of staircase analog signal, which is needed to be refined and being sent to the low pass filter, which is making it into ideal form and filtering the uh, small kind of variations, distortions or ripples in that staircase analog signal, and converting it into a pure analog signal. So this is how a digital signal processor uh, behaves on the side of the receiver. Now I will be focusing on some later topics in which there will be firstly a discussion on the purpose of the DSP, which is to remove the undesirable noise from any kind of signal, purify a signal from any noise, and uh, it is also being said that it is being used for various other applications as well. The DSP not only used for noise filtering but also for modulating a signal, demodulating it, multiplexing a signal, demultiplexing it, signal conditioning, signal mixing, and any kind of twisting and tilting and manipulation of the signal. The DSP is used for that purpose as well. Any kind of work which is being done by the analog signal processor can be achieved in a more better way than an ASP in the DSP. Now, what is the definition of the DSP? A DSP is a method of manipulating a signal in a digital form. Whenever a signal is processed in a digital form and there are some manipulations which is happening in the signal in the digital form and it is being processed in the digital form, any kind of signal, then it is being said as digital signal processing. We have uh, another topic which is the explaining the basis of the DSP, in which we have this block diagram. Before that, we will be doing a discussion on the processors which are used for the DSP. We have various kind of processors, which are some kind of normal processors, traditional processors used for all purposes, and we have also a kind of dedicated DSP processors. So early traditional processors were not of very much fast speed and do not have much memory. That's why they cannot be used for the DSP operations. And for that reason, in the early 1960s, we use some dedicated DSP processors. But nowadays, as you know, that we have 32-bit and 64-bit processors which are built in with reduced instruction set computing, and those kind of processors can perform all kind of DSP operations nowadays. The concept of the digital signal processing can be retrieved from this block diagram. You can see over here we have an analog signal which is coming on the side of the A to D converter. It is being converted into the digital codes over here, and we have a ROM which is storing the instruction of the DFT or the ZT, and we have a RAM which is getting the bits over here of the analog signal, and the DSP processor is getting the instruction knowledge and applying it on the data which is coming in the RAM, and then sending the data which is processed after directly as digital stream or can be converted from D to A converter into original analog output. So in that way we have achieved the processing of the analog signal in a digital way, and this is being said as digital signal processing. Now we can see some in depth of how the analog signal is converted into digital code in the A to D converter. Normally we have an analog signal coming, and this analog signal is having infinite number of time values, but the discrete signal has finite number of time values. So what is being going on over there is that analog signal, three processes are happening over here. First one is the sampling, which is the discretizing of the time domain. Second one is the discretizing of the amplitude domain. So the discretizing of the time domain is sampling, and the discretizing of the amplitude domain is quantization. And following the shape of the signal and connecting the points of the sampling with the quantized points, we follow the shape of the signal and we have a sampled version of the signal. And this sampled version of the signal is then coded with some quantizer, some 4-bit quantizer or 8-bit quantizer. Normally 8-bit quantizers are used, and then every shape of the signal, every point of the signal is represented by a digital code, and this is how a signal from analog form is converted into the digital form. We have various kind of operations which can be performed with the DSP. Some kind of complex mathematical operations can be performed. Some simple addition, subtraction, and multiplications can be performed. We have various applications of DSP which can be used for signal equalization, compending, phase shifting, mixing, signal generation, modulation, demodulation. As told earlier, these are different kind of terminologies which are used in the communication, electronics, and for that we can have some dedicated analog circuit. But in DSP we normally do their processing in the digital way in an ideal manner, and in that way we can perform a more ideal operation of these terminologies in the DSP with the help of a computer, as told in this block diagram of the digital signal processing. DSP processors in the early 60s were not very much sophisticated, and they cannot perform the real-time processing, which is very fast. So nowadays we have uh, good processors which are of 16-bit, 32-bit, and even 64-bit nowadays available, and they came across the world in the early 1980s. And after that, the processing of the DSP was nearly possible with these kind of microprocessors coming into play. Uh, DSP is a kind of technology which is involving some gadgets, some digital calculators, or involving the use of the microprocessors, and the dedicated DSP gadgets can be formed with the help of FPGA, which is Field Programmable Gate Array, in which we have virtual devices which are logically connected, not hardwired connected with each other, but logically connected with each other, and provides us a way in which we can form some customizable DSP gadgets for some dedicated applications. Like for image processing, we have one gadget, and for the video processing and other dedicated applications, we have various kind of DSPs. All can be made into play with the help of this FPGA technology. Now we have early DSP processors. We will be discussing about early DSP processors. What was the limitation in those DSP processors, and which is not a limitation in nowadays DSP processor. In the DSP processors early, we have von Neumann architecture, in which we have the stored program concept, which is that instruction is saved in the memory and then applied on the data. But in von Neumann, we have a kind of bottleneck, a kind of limitation, due to which there is a kind of great limitation in the execution speed, which is that we have only one memory which is dedicated for RAM and ROM applications. We have only that memory in which the data is coming as well, and the instructions are also saved in that memory. And for the processors to retrieve the instructions from the same memory at one time and then apply it on the data in the same memory on the other time, and it is kind of greatly limitizing the execution speed. So that is being said as a von Neumann bottleneck. But the later there was a architecture which is the Harvard architecture, which also involves the stored program concept. But we have dedicated memories for the ROM as well as for the RAM. The ROM is storing the instructions of the computer, and the data is coming in the RAM, and we have a processor which is performing the simultaneous operations, getting the instructions from the ROM and applying it on the data on the RAM simultaneously, and we can have some real-time and high-speed applications possible in those kind of uh, DSP processors which are following nowadays the Harvard architecture. As we can see, this is a Harvard kind of architecture in which we have ROM dedicated for data and RAM dedicated for data and ROM dedicated for the instruction, and the DSP processor is performing simultaneous operations over here. So as I told early that we can perform various kind of mathematical operations with the DSP. Uh, we can have addition, subtraction, multiplication, division, and some kind of complicated operations. The clock speed of the DSP processor can be as much high to 1 gigahertz and can be within that range of 100 megahertz to 1 gigahertz. The DSP gadgets which are performing various DSP applications are available in the form of RAM plus ROM plus DSP processor combination, or in DSP plus ROM combination only, or in DSP plus RAM combination only. And for the purpose of designing of the DSP gadgets, we use the FPGA as told earlier to implement customized DSP gadgets. Now we will be discussing on the DSP applications, and there the most uh, uh, frequently told application is the filtering, which is removing the noise from any signal, and the noise is removed because the transmitter is sending a signal to the receiver getting the signal with along with the noise, so it is necessary to remove the noise as told earlier, and DSP processors can perform this kind of filtering application, and we have various kind of filters which can be designed in the digital filter regime, which can be a band pass filter allowing some band to pass through it and reducing the rest, the low pass filter allowing the low frequencies to pass through it and reducing the high frequencies, the high pass filter allowing the high frequencies to pass through it and reducing the low frequencies, and the band reject filter, which is allowing some band of frequencies to reject through it and allowing the rest to pass through it. So we have all kind of operations which can be performed with the analog filters can be performed with the DSP filters in a far more superior way. They have better selectivity and their phase response can be controlled more easily with the DSP filters as compared to the analog filters. If we talk about second application, which is the compression, and DSP gadgets can be used for compression purposes. Uh, this idea came into play because if we have any kind of analog signal which is of about 4 kilohertz frequency, and if that signal is being sampled at the rate of Nyquist, which is multiplied by 2, then it is a kind of 8 kilohertz sample. And then if 8-bit quantizer is used to represent any sample, then it is a kind of 64 bits per second, which is a too much kind of gigantic data, and which is nearly impossible to store in the RAM of the computer, and we need some kind of supercomputers which are made with very high memory, and that can store such kind of data, but it is not feasible, and it is that data needed to be reduced by the use of some DSP gadgets. So we have various compression standards which are followed in the DSP gadgets. We have MP2 compression standard for a kind of image signal, MP3 compression standard for a audio signal compression, and MP4 compression standard for a video compression signal. And if we talk about the video signal, it is a kind of any video signal which is of 4 megahertz, which is far more data than the only voice signal. So it also motivates our scenario with reference to compression, that it is needed to compress the data with the ratio of 1 ratio 100, 1 ratio 1000, or even 10,000, and then that data is being used in the RAM, and on which we apply the ROM instruction by the DSP processor, and on the side of the receiver we have a process signal, and after that we can perform a reverse compression algorithm, which is a decompression algorithm, to generate the same data which was being compressed. So that is about compression. Now we have another application of the DSP, which is spectral analysis, which is very important as far as engineers are concerned, because any kind of signal is analyzed in the frequency domain, and then we can do some manipulation in that kind of signal. So for that purpose we have a DFT. uh, any kind of DFT instruction is stored on the RAM, and the DSP processor can apply this instruction on the data coming in the RAM, and then that data is being converted from time domain to frequency domain. And spectral analysis is basically the frequency domain analysis of the signal. And we have DFT, which is very much complicated and complex in operation and reduces our speed of processing real time and high speed signals. So that reason we have a faster version of the DFT, which is the FFT, which is the fast Fourier transformation. And the basic idea behind the fast Fourier transformation is that we divide any kind of big problem into small pieces problem and solve each problem uh, separately, and then we can retrieve the combined result, and this is by which we can do DFT in a very faster way in the FFT, which can be incorporated in the ROM instruction of the DSP processor to process and to do the spectral analysis of the real-time signal at a very fast rate. There are various other applications of the DSP. We have signal averaging, and in that application we basically have a kind of analysis on the signal which is received on the side of the receiver, and if the signal average is greater than 5 as told by the transmitter, then it will be a kind of noise present in the signal. So signal averaging is done by some gadget, some DSP gadget on the side of the receiver, and whenever the signal average level is higher than the level told by the transmitter, then it means that there might be some noise present in the signal and needed to be removed, and the DSP gadget dedicated for that purpose to remove the noise will be doing its own kind of work to remove it. And we can have also, we can save some different bit patterns of the symbols of the digital data, and we can generate any kind of signal according to our wish and whim in the DSP gadgets. And they can be doing the modulation, the kind of demodulation, the mixing, and we have some DSP gadgets which are performing these kind of operations, can be said as a software defined radios. Now, as we have also already discussed about DSP applications, DSP processors, and the basis of DSP along with its purpose and definition, now is the time to see some kind of applications of the DSP which are very much common, and how DSP works in those application scenarios which we will be following in this course. And the first one is the kind of filter applications. Normally there are two kind of filters in the digital regime, which are the FIR filter, finite impulse response filter, and the IIR filter, which is the infinite impulse response filter. In this uh, discussion we will be discussing about the FIR filter more in detail than the IIR filter. The FIR filter is a non-recursive filter, which means that it takes into consideration only the present and past values of the input for the calculation of its final output. And we can see over here the algorithm demonstrated in the form of a diagram of an FIR filter, and here that algorithm is elaborated in the form of mathematical model. And we can see over here that this is the present input and this is the past inputs, which are demonstrated by the delay lines, which are used particularly diagrammatically for that purpose to show some delayed signals, some kind of old signals. And after we have over here the filter functions which are used over here, and these are the filter functions for the low pass filter, and these would be different for the high pass, band pass, and band reject filters. The different filters we have designed in the FIR regime, these kind of impulse responses will be different, and we have different output which is coming on the side of the output. So IIR filter are those filters which are recursive filters, which are having the feedback loop involved in that in their algorithm, and these are the kind of filters which calculate the values of the output based on the present and past inputs and past outputs. Now we will be seeing about the spectral analysis. For the spectral analysis, we use normally the fast Fourier transformation, which is also being said as decimation in time, which is splitting up a large problem into small problems and then solving those problems and forming a kind of group results, forming a kind of butterfly group and stage results, and then we have some bits over here, and this is the algorithm of the FT analysis, which is the spectral analysis. And you can see over here we have the bits on the left hand side, and these bits are divided into different groups, and we have some kind of different results which are formed over here, and then we have the output, final output, which is coming over here. This is in the frequency domain, these are in the time domain, and we can form these complex domain results which are coming in the complex form. We can calculate their magnitude as well, we can calculate their phase as well, and in that way we can do the spectral analysis. Thank you very much.